Hey everyone, it is me, Steve, and today we are going to do a comparison with actual observation with prediction from Dial-A-Moon, and that's what this is from. This is from Dial-A-Moon, the picture of the moon here for January 31st, 2018, which was that super blood moon lunar eclipse. Now, I did do continuous video of this eclipse until the clouds moved in, and that will be linked below so you can look at it, and it has time hacks in it and everything, and it's continuous except for one point where I had to stop it to move the camera, but then I reset it and did another GPS and another time hack so you could reset it and figure out exactly what is what and when. But this is from Dial-A-Moon. There's the website below, and the great thing about this website is a couple months before the beginning of the year, they'll do the entire year at 1 hour increments. And that's great. That's awesome because it's a prediction that you can use to see if it matches observation from your video and photos that you take. Now, I took from my eclipse video, I took this screenshot. Here's the information on the right. That's the time. Now, like I said, Dial-A-Moon only does even hour increments in universal time. So you have to remember that. Where I am, that's 6 hours ahead. So universal time for me is actually noon, not 6 a.m. All right, so you have to compensate for that. So be aware of that because it does it all in universal time. So this is the screenshot I took at that time, and we are going to compare it with the model of the moon passing through the Earth's shadow and see if it matches what we observe. And here, this is the apparent direction of Earth's shadow at my latitude. This is the direction it came in at because my tripod was set to level. Now, it only has one bubble level, so this will probably be off a couple of degrees, and it actually will be. But I actually got pretty close. But so the shadow is coming in from my upper left, and that may seem weird, but I am not at the North Pole, nor am I at the equator. So the moon's apparent angle tilt from its actual orbital plane is going to look different with your latitude. I hope I worded that okay, but anyway, let's get into it. So this is the Dial-A-Moon. And you can see the red box down here. I'm going to zoom in on that real quick. See, 12 o'clock universal time. You can't do more than even hour increments. So I was at 6 a.m., so that's close, or I was at 6 a.m. and 11 minutes, so that's closer to noon than 1300. So that is just a zoom in at that. And the great thing about this too is across the moon it shows a 2-scale model of the Earth-Moon distance. Well, the Earth's orbit is not circular, it's elliptical, so sometimes it's closer, sometimes it's further away, hence the supermoon and micromoon thing. And this time it was a supermoon, so we're going to zoom in on that real quick. So our perigee, we're really close to where perigee is in the orbit. Semi-major axis, that's the average distance the moon is from the Earth in Earth diameters, or and apogee here is its furthest away point. I didn't confuse those, did I? Perigee, apogee. No, I didn't. Good. All right. So now there's that. I'm not going to deal with what's in the lower left-hand corner because it has to do with subsolar and sub-Earth points, and it's not really relevant to this discussion. So let's go to the upper left here. Okay. Now this is a not to scale model of the distance that the moon's orbit is from the Earth. Now, the Earth is to scale here, and the moon is to scale relative to the Earth, and the eccentricity of the moon's orbit is to scale. The only thing here that is not to scale is the distance that the moon is from the Earth, and that's fine because you get it on the other part. So this was my actual latitude and longitude, and I'm only going to be working with whole degrees here because my program is not really accurate to any significant decimals, but it should be pretty close. So that's my location, and the yellow arrows here are indicating the rotational direction of the Earth on its axis and the directional movement of the moon through its orbit. Now, I'm only taking a snapshot in time, so we don't really have to worry about these motions because it's just a 1-second snapshot. And my line of sight at that time was basically here. There's the direction of the sun, and as you can see, The full eclipse was really close to sunrise for me, and I didn't get totality, and I would have only been able to get like a minute of it anyway because it would have set, but I didn't get totality because the clouds moved in about 10 to 15 minutes beforehand. But you take what you can get, right? And you can see that in my other video. All right. First, we have to understand some things here about how the moon actually moves through space with the Earth. So as you're looking at this, this is as if you're looking at the Earth from the sun. I just put a picture of Earth here. All right, it's not specific to any latitude, longitude, orientation, or anything. It's just so you can see how the moon is going to be blocked by the Earth's shadow. Remember, this is as if you're looking from the sun. We have the ecliptic. What's the ecliptic? The ecliptic is kind of this baseline we use. It's the orbit the Earth takes around the sun, and since that's our reference point, we just make it special and call it the ecliptic. However, the moon orbits the Earth, and it does not orbit on the ecliptic. Its inclination is 5.145 degrees, or about 5 degrees. Now, I'm going to show you here how the moon is moving in its orbit as it's going to pass behind the Earth during lunar eclipse. Now, this 5-degree inclination is usually high enough where the moon is not going to be within Earth's shadow, but during a lunar eclipse, it is. So we're just going to go through it here, and I'm just going to show you as it moves. There, the Earth blocks it. Now it's behind the Earth, and now your lunar eclipse is ending, and it comes out the other side. So I just wanted to show you that real quick to show you how that eclipse occurs. Now, the moon is tilted on its axis, but relative to the ecliptic, it's only like 1 degree. So it's not really significant. So here's my screenshot again, and that gives me my azimuth and the altitude. My azimuth and altitude were taken from a handheld Barton compass, so they're off plus or minus a couple degrees. But the time is exact and the zoom is exact. All right. I am going to use Tycho crater as my reference point throughout this. I'm also going to use it from the Dial-A-Moon snapshot that you saw, because I'm going to compare the prediction to what I observed and see if these line up, and show you that there is no, it doesn't, even though it looks weird that the shadow's coming from the north or from the upper left, it's totally expected because of my latitude. All right, so now we're going to drop the Tycho crater, but the dot is still there. All right, so now basically how I showed you how the moon moves behind the Earth, and the shadow that the Earth casts on the moon during the lunar eclipse is what gives us a lunar eclipse. I've taken the Earth off here just so you can see the shadow. Now, the Earth's umbra is about 2.6 times the diameter as it appears from Earth, because the umbra shrinks as you get further away from the Earth. Now, the Earth is about 4 times the diameter of the moon, but its umbra at the moon's distance is only about 2.6 times, plus or minus depending on where the moon is in its orbit, but that's close enough. All right, and here's in the Earth's shadow on the moon at 6 Central Standard Time, or that 12 Universal Time. So this, I'm going to take this and try to line it up with my actual still shot that I took from my camcorder video. And down there's the reference where I got the 2.6 times from. All right, so here it is. We take it. All right. Now we have to do some things about this. We have to orient the moon as it appeared to me in the sky and see if this lines up, because this is just based on the orbit, as if you're looking on the dark side of the moon, or on the dark side of the Earth towards the moon during the eclipse. That's what this is supposed to be. So that would represent that. So what we need to do is we need to figure out our angles. My latitude is about 42 degrees, so we make an angle here 42 degrees. Well, we can complete the rest of this triangle easily, because my tangent will be perpendicular to that 42 degree angle, which will give me 90 degrees. My tangent in this case is going to equal my horizon, and the complementary angle is 48 degrees in this case, because all angles of a right triangle have to add up to be 180. If I know my 42 and I know my 90, I know that last one's 48. It's a simple math, all right? So I'm going to take this and orient this now so you can see to where my horizon is level, all right? So first I extend my tangent at that 42 degrees. I extend it out to represent my horizon, all right? Now we need to level our horizon. That's what I've done here. I've taken that. This is a photo excerpt from that previous slide I just showed you. So Dial-A-Moon predicted lunar appearance at about 6 a.m. Central Standard Time / 12 a.m. Universal Time for my latitude on January 31st, 2018. So this is what the prediction is, all right? Does it match my still shot? Here's my still shot. There's the date and time it was taken. All right, now we're just going to move it slowly, okay, towards the moon. And my transparency here is at 33%. We're going to move it over a little more, and there we go. Now they overlap. This is really close. As you can see, there it is off a tad. If you zoom in and go to the 2 Tycho craters that I highlighted, we have about a 2-degree. I'm off about 2 degrees, but you know that could have been my tripod not being exactly level since it's only 1 bubble level, or you know that. It's probably what it was. And plus, I'm not exactly at 42 degrees either. So the predicted appearance of the eclipse at 6 a.m. Central Standard Time is off by about 2 degrees of my observation at 6:11 a.m. So we're really close here. So that's why that shadow looked like it was moving from the upper left to lower right if you were at my latitude. But if we compensate for that, it works. It's fine. So just to show you real quick, here is the Dial-A-Moon website. Okay, it's a great place, and like you can see here, you enter your month, your day, and your UT hour. Now remember, UT hour is in 24-hour system, so you can't add PM. So your 3 o'clock, or so your 1 o'clock PM would be 1300. Your 3 o'clock PM would be 1500. You have to just enter that, and like I said, it does only even hour increments. So anyway, that's it. I hope you learned something. Feel free to comment or ask questions, and thanks for watching.